Lastly, we'll talk about ellipses and the properties of an ellipse. We're neglecting to go over hyperbolas because it's less often used in math. I think the most often equations that you get in precalculus would probably be parabolas and ellipses. Ellipses have very similar details to a circle, other than the fact that the axes now have different lengths. So right here we have like a minor axis because it's like shorter going this way than the major axis, which is longer going this way. The equation of ellipse is as follows right here. For a horizontal ellipse, this is for a vertical ellipse. You notice the thing here that changes is the denominators. This ends up being b squared, where this used to be a squared, and then this is a squared, where this used to be b squared. So the actual definition for an ellipse, though, other than like the simple one of it's an elongated circle, is that an ellipse is a set of all points such that the sum of the distances between 2 points, called the foci, or is constant. Basically meaning that, like, if you look at this triangle with D1 over here and D2 right here, it's an ellipse if these two distances, which are different, are always constant no matter where we move this point. So hypothetically speaking, if I moved my point over here and my D1 was this distance and my D2 was this distance, they would still add up to the same value. And that should be able to be done everywhere, regardless of if the point is here or if it's like here. You know, the two distances will always have the same value. Then you have an ellipse. The vertices of an ellipse are the points where the ellipse intersects the line through the foci. So the foci is like where these distances are coming out of. The major axis is the line segment between the two vertices, or I was saying it's along the long side. Minor axis is along the short side, perpendicular to it. The length of the major axis is 2a, where the length of the minor axis is 2b, because a is the radius of the major axis, so 2a would be like the diameter of the major axis. And similarly for the minor axis. And that last point is the one that I was making about the horizontal and vertical. The major axis can be vertical or horizontal depending on where a squared is in the denominator, or under the ellipse in the standard form of the equation. So it can be vertical or horizontal depending on whether, again, a or b is in the denominator at which point. Here are the properties for an ellipse. Horizontal ellipse looks like this, whereas a vertical ellipse looks like that. Almost, well, it is exactly the same. Of course, I think that's about 0, 0. Major axis has a focus of a h plus or minus c k, and then vertical is k h k plus or minus c. You can obviously tell that the horizontal just has its focus and vertices boosted along the x direction, whereas the vertical has its vertices and focus boosted along the y direction. The only time that is different is when you're talking about the intercepts on the minor axis, because the minor axis is perpendicular to the major axis where the focus and vertical vertices lie on. So since the minor axis is perpendicular, its coordinate is boosted along the y, and the vertical's coordinate is boosted along the x because they are on different axes. So hopefully that has given you some perspective on the properties of an ellipse, and we will try and analyze one right now to really hammer this point home. So in this example, we're walking through, we can find the center, foci, vertices, and major minor axis of an ellipse if we get the standard equation given to us. So here's the equation for the ellipse given to us. The center here is at -1 and 1, and I know that because I have x plus 1 here giving me -1 and y minus 1 here giving me +1 for the center. If you use the definitions that we brought up, let me back up. So we have A and B and the bottom. Knowing that this is either going to be A or B, we could take the square root. And I believe since this is larger, we have a vertical ellipse. Square root of 48 is 8. So I have A is equal to 8. And then the square root of 64 is 6 root 3. Then you can use the a squared plus b squared is equal to c squared fact to get this thing. So you have c is equal to 4, a is equal to 8, c or b is equal to 6 root 3. You know what h and k are because h is 1 and k is equal to -1. So we can find our foci fairly straightforward from there because we know that it's along the major axis, which is going to be at the same level as the center. So they're all going to be at -1. Finding the foci and vertices, if you recall from the last slide, is since this is a vertical, we're gonna do k plus or minus c on finding these foci or vertices. So I'd have -1, or I'd have -1, 1, and then right here is k, so I do plus or minus c. So if and c here is 4, so I'd either have -1, 5, or -1, -3. Now for the vertices, if I remind myself over here, is also hk plus or minus c. It doesn't seem right. I think this is actually supposed to be a. I'm thinking that this is supposed to be a. So finding the vertices would be a similar process. However, we'll do hk plus or minus a. So right here, I'll do still -1 because that's h, but now I'm doing plus a. So k, which is 1, plus a, which is 8, would give me 9, and then minus a, which is 8, would give me -7. So that's how you find the foci and the vertices. And then the major axis is the vertical axis, multiplying 16 by 2 to get, 16 all right, sorry, 2 by 8 to get 16. And then the minor axis is 12 root 3, doing the same thing for B. Because recall the major axis is 2A and the minor axis is 2B. So by just getting the standard equation for the ellipse, we were able to figure out what the center was, what the major and minor axis were, what the foci and vertices were. And it's a very good practice to be able to deconstruct equations like this and get important information out of it.